After we went through some examples of transforming a function from time domain to Laplace domain, I will give some illustration about some properties in Laplace transformation. If you still remember, so there are two tables for Laplace transformation. The first one is a table that lists all of the properties of a Laplace transformation. There are few properties here, but I will only discuss few of them. I will discuss 5 of them in particular here. I will discuss linearity, differentiation, integration, and the two most important properties, the one that I mentioned at the beginning of this course, the final value and initial value theorem. So let's start it with a linearity property of a Laplace transformation. Let's imagine you have two functions, ft and gt, and if you have a function that is combination of these two functions, let's call it ht, and ht is equal to ft plus gt, and if Laplace of ft is equal to fs and Laplace of gt is equal to gs, then Laplace of ft plus gt will be equal to fs plus gs. So this is very simple concept. If you have two functions f and g, the Laplace of f plus g will be equal to the Laplace of f plus Laplace of g. Okay, it's pretty straightforward. That's the first property that I want to mention. The second one is the differentiation property. This is slightly more complex, but don't worry, it's not that complex. So let's consider a function of x again, xt, where the Laplace of xt is equal to capital Xs. Now, looking at this second property, if again xs is a Laplace of xt, then the Laplace of the nth derivative of xt will look like this, and this Laplace counterpart of the nth derivative of xt can also be expressed by xs, where xs is the Laplace of xt. So this is a case when we are looking at the nth derivative of x. Let's take a simpler case here. So I want to find the Laplace of the first derivative of f. First derivative of ft, let's say here. So looking at that property here, I show it again, that particular property, the property of differentiation in Laplace transform. When I'm going to evaluate the Laplace of the first derivative of f, that means the n is equal to 1 because it's the first derivative. So if n is equal to 1, then I just simply have to substitute 1 to all of the n's in this Laplace counterpart in this differentiation property. If I replace n with 1, so the Laplace of the first derivative of x, in this case I denote it as f to make it different than the one displayed in the table. The Laplace of the first derivative of f will be equal to s times fs minus f when time is equal to 0. So how do I obtain this? This is obtained by just replacing all of the n's here by 1, because I'm evaluating the first derivative of ft here. So again, then the Laplace of the first derivative of ft will be equal to s fs minus ft when t is equal to 0, where fs here is the Laplace of ft. Okay, so if I know the Laplace of ft, I can easily find the Laplace of the first derivative. Let's take an example here. I want to find the Laplace of the cosine t, in which I know that cosine is the first derivative of sine. Okay, so I can rewrite this expression Laplace of cosine t as this expression Laplace of the first derivative of sine t. Since we know that cosine is the first derivative of sine, I can replace it into this form, and then using this property, I can find then the Laplace of the first derivative of sine will be equal to s times Laplace of sine minus sine of t when t equal to 0. From the second table of Laplace, we know that Laplace of sine t is equal to 1 over s squared plus 1. So I can replace this term Laplace of sine t with 1 over s squared plus 1. So I will just simply multiply s by 1 over s squared plus 1 minus sine of 0. And sine of 0 is equal to 0. So Laplace of cosine of t will be equal to s times 1 over s squared plus 1, which is equal to s over s squared plus 1. So this Laplace counterpart of cosine t can be found by using the second property of Laplace transform. Now let's take a look on another case when we want to find the Laplace of the second derivative of ft. How to do that? Just looking at this property again, and then I will replace all of the n's here on the Laplace domain by 2, because I want to evaluate the Laplace of the second derivative of ft. So I just replace all of the n's here by 2. If you look at these properties, I will end up into this function. The Laplace of the second derivative of ft will be equal to s squared fs minus s times function of t when t is equal to 0 minus the first derivative of f when t is equal to 0. If I know the function of t and I know the Laplace of ft, which is fs, I can also find the Laplace of the second derivative of ft using this expression. And then I can do this for any degrees of differentiation of ft until degree of n by just looking at this property. So this is how to make use of the second property of Laplace transformation, which is the differentiation property, to find the higher degree differentiation in Laplace counterpart. The next property that I want to discuss is the integration property. So it's similar to the previous property of differentiation. Let's say if I have a function of x in time domain, and if I know the Laplace of xt, I will also be able to find the integrate of xt in the Laplace domain. So let's take a case here. In case I want to find the Laplace of the integral of ft dt. So how do I do that? I will just use the third property of Laplace transform. How to do that? The Laplace of the integral of ft will be equal to fs over s, where fs is the Laplace of ft, plus 1 over s times the integral of ft when t is equal to 0. So by just knowing the Laplace of ft, you can also find the Laplace of the integral of t. Let's take this example again here. So let's take a case when I have ft. Ft is equal to t when t is 0 and greater than 0, and ft is equal to 0 when t is negative. This function is called as a ramp function sometimes. So ft basically is linear of time. And then you know that the first derivative of t, linear function of time, will be equal to 1. Or 1 basically is a step function. Still remember about step function. Step function is when the value of the function is equal to 0 for negative time, and the function will be equal to 1 when time is equal to 0 or greater than 0. So this is the step function, which is basically step function is the first derivative of the ramp function. Just as a side note for you, step function in some books, it is presented as a function of 1 as function of t. So some books, they mention step function as ust. In some other references, they refer step function as 1t or just simply 1. So don't get confused. Sometimes I might write 1 to represent a step function. Sometimes I write it as 1t. Sometimes I write it as ust. But all of them refer to the same function, which is the step function. So let's get back to the integration property. As we just discussed, basically step function is the first derivative of the ramp function. Now, if I want to find the Laplace of the ramp function, I can evaluate this expression. I can find the Laplace of the ramp function by finding the Laplace of the integral of step function. And then integral of a step function, I can express it as follows, because this will follow the integration property, the one that we just discussed before. So by evaluating this mathematical expression, then you can find the solution, which is equal to 1 over s squared, and basically 1 over s squared is the Laplace of the t or the ramp function. So this example illustrates the application of the third property of Laplace, which is the integration property. Up to this point, we discussed about how to transform time domain function to Laplace domain and vice versa. We also have discussed the property of Laplace transformation, but I haven't touched at all on what is the application, what is the usage of this Laplace transformation. Well, we touched a bit when we were mentioning that Laplace transform is used to solve the differential equation. But how to use this Laplace transformation in real-world application? I will illustrate it by looking at this slide. So imagine I have a system that looks like this. So this is basically a mass spring damper system. Imagine I have a mass. I hang the mass through a spring and a damper B to a ground. So this mass is supported to the ground through the spring and the damper K and B respectively. If you look at this schematic diagram, this looks like a wheel of your motorcycle if you hang your motorcycle. So the wheel of your motorcycle, one of the wheel represent the mass in this schematic diagram, and the spring and the damper basically are the component of your shock absorber. It contains a spring and the damper. So in this case, the mass of this block is m, the stiffness of the spring is k, and the damping coefficient of this damper is b. If I perturb this mass, let's say if I shake this mass, if I touch this mass, or if I just simply disturb it, the mass will shake, right? The mass will shake, and the displacement of this mass is represented by the variable x. The motion, the movement of this x, the mass m, can be represented by this following equation of motion, where again m is the mass of this block, b is the damping value of the damper, k is the stiffness value of the spring, x represents the motion of the mass. So if you want to see how the mass is vibrating in time, you have to solve this equation of motion. Just for your information, how to derive this equation of motion of this mechanical system, we will discuss it later on in the next topics. But for time being, just accept it. This equation of motion will represent the motion of the mass m. So x again is the motion of the mass m. So if you solve this equation of motion, you can estimate how the mass will vibrate in time. So let's assume after I perturb this mass, the displacement of this mass will be at xi. The velocity of this mass just after I perturb it will be equal to vi, the velocity of the mass. And then I want to find how the mass will displace in time by solving the solution of x. So how do I do that? I will Laplace transform this equation. Let's say the Laplace of x, the solution that we are looking for, is equal to capital XS. So the third term here, after I Laplace it, it will become k times capital XS, the Laplace of xt, right? The second term is bx dot b times the first derivative of x, and then I will transform it in a Laplace domain. But remember, because of the differentiation property, the second property in Laplace transformation, the Laplace of x dot, if you refer to our discussion in differentiation property, the Laplace of the first derivative of x will be equal to xs minus xt when t equal to 0, right? You still remember about this. If you don't, please refer to that slide, the slide that we discussed on the differentiation property. So the Laplace of the first derivative of x will be equal to xs minus xt when t equal to 0. And then I have to multiply it by b. And then the first term, I have mx double dot m times the second derivative of x. Again, using the differentiation property, the Laplace of the second derivative of x will be equal to s square xs minus s of xt when t is equal to 0 minus the first derivative of x when t is also equal to 0. So at this point, I have already transformed this differential equation into Laplace transform, into Laplace domain. So from this point, I just simply have to substitute all of the variables that I know. The xt when t equal to 0 is xi. The first derivative of x when t is equal to 0 is equal to vi. So I will replace this x0 with xi, this as well, and then I will replace this x dot 0 with vi. Okay, and then after some mathematical manipulation, I can get xs. Xs will be equal to this expression, where xs is again what? Xs is the solution of x, solution of this differential equation in Laplace domain. So at this point, essentially, I get the solution of this differential equation. But remember, the solution is still in Laplace domain. I have to use my Laplace table to convert this solution to time domain. So from there, you can find the solution of this differential equation, which corresponds to the displacement motion of this mass. Okay, so that's how to solve the solution x from differential equation. Okay, in the next following slides, I will discuss the two more important properties of Laplace transformation. The first one is final value theorem. What is final value theorem? Final value, let's talk about final value first. Final value, if I have a function ft, some function will have final value. So let's take an example of this function. If you look at this function, this green plot is a function of t, is ft. If you look at this plot, this function has a final value. What is a final value? Final value is a function, is a value of ft when time approaches infinity. Some functions might have a final value. For instance, this function will converge to one specific value when time approaches infinity, right? So this function has final value. Some other functions might not have a final value. What is the example of a function that doesn't have final value? Let's say a parabolic function. A parabolic function, if you have parabolic function, the function will go to infinity when time approaches infinity. So that kind of function doesn't have final value, because when time approaches infinity, the function will go to infinite value as well. But in this particular example, this function has a final value. For instance, you want to find the final value of this function. You can find the final value of this function if the function has a final value, of course, without a need of knowing the function itself, as long as you know the Laplace transform of the function. How to do that? So if you want to find a final value of a function ft, so the value of f when t approaches infinity, you don't need to know the function of ft. You can evaluate this final value as long as you know the function of fs, the Laplace of ft. So you just have to evaluate limit s to 0 of s times fs. This will show you the final value of ft. But of course, this theorem is valid only if your function has a final value. As an example, the parabolic function will not have a final value, so this theorem will not be applicable. How do we know if a function has a final value or not? You know whether a function will have a final value if you know the function in time. But if you only look at the Laplace counterpart of that function, how do we know if the function has a final value or not? It is very simple. A function will has a final value only if all of the poles of that function in the Laplace domain are negative. All of the poles are negative. You still remember what pole is? We discussed that before. Pole is the function of s that will result your function in Laplace domain to become infinite. So if I go back to the final value theorem, your function ft will have a final value only if all of the poles of your function in Laplace domain are negative. Or you can have one zero pole. So you will have final value only if all of the poles are negative, or at most you have one zero pole. If you have two zero poles, then you won't have final value. So all are negative, or at most you have one zero pole and the rest are negative. Then you will have final value. So let's take an example of this. Let's say I have a function of ft, but at this point I don't know what ft is. All I know that the Laplace of ft is equal to this 2 divided by s plus 2. If you look at this function in Laplace domain, this function will have two poles. Remember what is pole? pole is the value of s that will cause this to be infinite. From this function, you have two poles. The first pole is 0, because when s is equal to 0, then you will have 2 divided by 0 times 2, which is infinite. That is the first pole. You also have the second pole when s is equal to negative 2. When s is equal to negative 2, you will have 2 divided by negative 2 times 0, which is infinite. So in this example, in this function, you have two poles, 0 and negative 2. So you have one 0 pole and the rest are negative, which is only negative 2 in this case. So in this case, then your function here will have a final value. That means you can evaluate the final value of your function by using the final value theorem. Final value theorem says the final value of ft will be equal to limit s to 0 of s times fs. So I just simply substitute this fs to this. So I have to multiply s by 2 over s times s plus 2. This s will cancel this s. I will end up into this expression, limit s to 0 of 2 divided by s plus 2, which is equal to 1. So this ft will have a final value of 1. Let's take a second example now here. Let's consider another function ft where the fs, the Laplace counterpart of ft, is equal to 2 divided by s minus 2. Now, by applying final value theorem, you want to evaluate the final value of ft. You use this final value theorem, you substitute 2 over s minus 2 to this fs, and then you calculate the final value. This s will cancel this s, you will end up into this expression, so you can find the limit s to 0 of 2 over s minus 2, which is equal to negative 1. At this point, you might have a notion that the final value of this ft is equal to negative 1. But be careful, if you look at this function, the two poles of this function are 0 and positive 2. You have positive pole. Positive pole means you won't have a final value. So even though you can find the value of negative 1 by evaluating the final value theorem, this negative 1 doesn't mean a thing, because this function should not have a final value. So negative 1 here is a wrong answer, because your ft should not have a final value. So remember, before you evaluate a final value of a function, you need to check whether your function will have a final value or not. So these are the story about final value theorem. One more property that I want to discuss is initial value theorem. What is initial value theorem? Is similar to final value theorem. Final value theorem is a technique to estimate the final value of a function. Initial value theorem is a technique to estimate an initial value of a function ft. What is initial value? Final value is a value of a function when the time approaches infinity. For initial value is a function, the value of the function when time is equal to 0. So that is different. And any function, no matter you have a positive pole or negative pole, any function should have initial value. So for initial value theorem, it applies to any cases. You don't have to check the location of the poles of your function. You just can apply this theorem to any function. And then how does initial value theorem say? Initial value of a function, you can evaluate it from this expression. You can just find limit s to infinite of s times fs. So if you want to estimate initial value of f, you don't need to know what ft is, as long as you know what the Laplace counterpart of ft, which is fs, you can estimate the initial value of ft. So there is no restriction of initial value theorem. It can be applied to any function, no matter you have a positive poles or negative poles. I think that's all for this session. Just two remarks for final value and initial value theorems. These theorems will enable us to predict the system behavior in time domain function without need to transforming the function in Laplace domain to time domain. You can immediately predict the system behavior in terms of initial value and final value by just looking at the function in Laplace domain. And these two theorems is pretty convenient to just doing quick check on the behavior of your system on the final solution of your differential equation. As a summary of what we have already discussed in this session, so we have already discussed how to define dynamic system and its types. We also discussed already how to analyze the required mathematical background for dynamic systems. Okay, thank you for your attention for in this session.